So good morning. We will start this last morning with a presentation from Evan Hoffman, NASA USA, about laser safety at NASA new laser ranging stations.
All right, good morning everybody. Thanks for coming on Friday morning, first presentation. So I'm going to be talking about laser safety at our new ranging stations and laser safety a little bit in general. One of the valuable lessons I learned here, and one of the reasons I'm really glad we reconnected here, is I learned a lot just by talking with you folks about how we approach laser safety. There's a wide variation of tolerance to risk, I learned. So start here. So I'm going to start with this little video here. There it is. Video for three reasons. We've been doing laser safety for a long time at NASA. And it's been on our minds for decades. Number two, we'll use anything at NASA until we can't use it anymore, so it's back in this presentation. And also, if you know this person or you're in the audience, let me know. I'm trying to find out who this guy is. He was at Goddard, I suppose, in the late 70s. I think this is the 30-inch telescope at GJO, so yeah. And if you want to see the whole video on laser safety, made sometime in the late 70s, I believe, the hyperlink is up here, so have a look, and there's more of that baseline in there too. Okay, so when we approach laser safety, and when I started to have to really think about protecting aircraft and ground people, it's hard to know who the authority it is and where to start and what standard you're using. There's just many standards that are available in laser safety. And there's a list of them, and they vary by locale and department, and even within locale, different departments can dip their toes into laser safety. So it's kind of it can be very difficult to know what rules you're supposed to follow, and when you're actually blessed by whoever authority you have to range. So that's been a very long and iterative process at NASA, and I just listed a couple that we touch at NASA and also internationally as we partner with our Norwegian friends. So for our new stations, our requirements are a little stricter in terms of they need to be able to operate eventually autonomously. So the idea is, after some development, these will be autonomous systems and should be able to protect people without human intervention. So they have to support local and fully automated operations, aircraft safety and ground safety. They have to be fail-safe. And one thing that we have to do at NASA specifically is try to keep it separate from the operational software that actually does the ranging and the decision making. And why is that? Because according to the NASA Software Safety Handbook, and we have handbooks for almost everything, safety critical software has to undergo a lot of testing and a lot of rigorous analysis, which is very time consuming and very expensive. So in order to better develop the operational software without causing the expense or the analysis to blow up, we made a decision to separate it completely. So there's no software involved with laser safety decisions. It's baked in, very simple firmware type process. So these are just some points of how different hazardous softwares and mishaps are defined. If anybody's interested in what the laser safety, the critical, or the software safety handbook says, it is available online if you want to take a look at it. And this is a public domain Pandora over here. Okay, so our strategy in the software was to eliminate any safety-reliant features in the operational software. If we do identify anything, we isolate it from the operational software and make it as simple as possible. I discussed, I'm not going to go into this too much, but this is just a general block diagram of our laser safety subsystem chassis, showing just very simple. We tried to make it as simple as possible with different interlocks and sensors on doors and pressure pads and the different entryways. Basically just 1 or 0, no complicated information to decide whether to cut the laser or not. So it's might be hard to pull out from this block diagram, but that's kind of the strategy we have here, and general status information passed to the operational software. Okay, so the equipment we're using, we've developed a lot of it in-house, tested by KBR. I forgot that they're no longer KBR Wiley, but I put that on there. But anyway, so it uses a lot of heritage that makes safety people very comfortable. When they've already blessed something, you can continue with the same or similar design, but we had to update a lot of it for future autonomous considerations. And this is just a general picture of SGSLR and the different interlocks and safety places where we had to consider protecting folks from laser exposure. So I just wanted to show where some of the sensors would be placed. On the optical bench, we have 2 blocks that are what we use to attenuate or block the laser. There's a laser block and an attenuator for ground calibration to make it eye safe going out to the target, just placed up on the laser side here. In Jan's talk on Wednesday, she showed a bit of the laser table here, but I just wanted to show where we're putting the block. So it's just 2 simple blocks that fall into place when a power is cut, so they're fail-safe in that way. Okay, so when going through some of these things, we had to consider a lot of aircraft detection methods, and given some talks that were given yesterday, I should maybe put IR cameras up here for other consideration. But just some of the different modalities we've explored and we use for some of our systems that a lot of you are already very familiar with. We mainly have active radars and mount observers currently, except at our Apollo Lunar Laser Ranger, which uses the transponder TBAD, which is a directional transponder. So the pluses and minuses of each of these, they all have their strengths and weaknesses, and we really had to consider what to use. It took a long time to convince our safety folks that we could move away from mount observers, for example. So once you get something accepted, you kind of want to go with it as much as you can. And also site placement, we have to consider the airspace around the different sites that we have. So I just put up 2 examples. This is airspace around GJO in DC, and this is MJO, Texas. You can see one is a lot more active than the other. It might lend some decisions as to what you can get away with risk-wise. Okay, so what we're using now, I mean, each one has their pluses and minuses. Active radar doesn't require cooperation from the target, but it doesn't play nice with VLBI and can be expensive. The others require actual interrogation of the aircraft or what have you. So they require some cooperation, which many places that's not a problem. And some places say there's military craft that wouldn't actually don't want to advertise. That might be a problem depending on who you talk to and who your safety officer is, and if you have a safety officer. So there's a lot of variation in here that we're learning. But Neolison, our first site, is going to just use an ADS-B receiver because there's no radar allowed by law, and I'll just talk about that briefly in a moment. Oh, here it is. Okay, so at Neolison, this is a picture of the dome in Neolison installation. So we're replacing the radar with aircraft avoidance system that's being developed by the Norwegian Mapping Authority. It's going to be our first dipping our toes into using exclusively ADS-B for aircraft avoidance. I know a lot of you do this already, but this is a step that we haven't taken at NASA, or we haven't had familiarity with in terms of our safety culture. So it lends itself to this site specifically because, especially since the air traffic is much lower than, say, GJO. And for the Neolison shelter, it's a little different than our regular SGSLRs. The shelter was built by NMA, and it's this very pretty wood structure here. So we have to think about different entry points, but the general system should be about the same, kept very simple. Okay, so going back and forth and partnering with the Norwegian Mapping Authority really showed us what it takes to actually blend the two safety cultures and the challenges that comes with that. So I think developing the interface control document and the requirements for their system, going back and forth, really helped us refine what our requirements were. Okay, I think I'm probably running a little long, so I'll just say that there's a poster talking specifically about the ADS-B that's going to replace our radar that is still out there if you want to take a look at it, and this is the title of that poster. So yeah, I think that's about it. That's it. Thanks.
All right, thanks, Evan. Do we have any questions? All right, Andrea.
Thank you. Quick question. Do you use a redundancy concept in your laser safety at your sites? For instance, TBAD plus ADS-B, or you just rely on one sensor?
Right now, we're investigating combining some to play on the strengths and weaknesses of both, like radar and ADS-B, so that we can get the lower elevation aircraft. But right now, we only have single detection systems. But we are looking into whether we can do that. And I'm sure we can, but we're developing it. So, yeah.
Any other question? So is the system ready, the hardware that you have shown to, so to say, digest multiple inputs, e.g. from radar and ADS-B, or that's something you would need to incorporate as well?
So the system is designed to ingest multiple inputs. It's made very modularly. So the radar basically gives a 1 or a 0, block, no block, which allows the AAS that the Norwegian Mapping Authority is developing to just plug in. So we designed it that way on purpose so that we could swap out easily different sensors and things.
Okay.
Yeah.
And I guess the laser's eye safe with the 60 centimeters?
What's that?
With the 60 centimeters on the transmit path, the laser's eye safe?
No, it's not eye safe. It's
Okay.
not, the laser is not 60 centimeters. So.
Okay, sorry, what was the diameter of the primary mirror?
Well, it's not filling the whole aperture.
Okay.
So, so it wouldn't be eye safe out of the telescope.
Okay. Anything else? Okay, I think that's it for the first presentation.